So in today's video, we're going to study a little bit about electricity today. I'm going to cover the basics. Some of the basic knowledge that you'll need to work with HHO gas and electrolysis. And you don't need much, I'm going to cover some of my electrical circuits here, and then we're going to cover this kilowatt system here. This shows you how much electricity you're pulling, and that's very important to understand that. You need to know how much electricity you're using. You're probably asking yourself, what's this frog doing in here? Well, back in the old days, about the 1820s, before the voltmeter was ever even invented, this is how Michael Faraday used to test electrical circuits. He used to put electrodes on a frog and hook some wires up to it, but they'd kill the frog. It was a very sad ordeal. We're not going to kill the frog today. This guy's actually my little friend. He eats all kinds of stuff. I feed him. I take care of him in my laboratory. My buddy. But anyways, we're going to cover basic electricity today. See, and back in the old days, when it used to rain and they seen the lightning, they figured, well, that's where the electricity's coming from. That's what they thought. They used to think it was coming from the frogs. And in the Egyptian times, here, let me show you in this folder right here. So you can see in this picture, they're using a frog to measure resistance in ohms. You know, so you have to pay attention to some of that stuff. So we'll cover what we can in this video. I'll do the best I can. We're just going to cover the basics. Sometimes it's good to go back to the basics, you know. So we'll continue on here. I'm going to show you guys a lot of the different tools that I use in my laboratory. When you're working with a wet cell or a dry cell, you're working with oxyhydrogen gas and electrolysis, it pays to have a bunch of test leads. And I use these leads, they're indispensable. I have some of them, I've cut the ends off. Geiger counters, radiation detectors, you can use that for high-speed particles like electrons and beta particles. That's not necessary with electrolysis. This is just a tool that I use in my laboratory to show some of the other things about the table of elements. These are the most important things that you'll need. Some basic books. You know, basic electronic books, nothing complicated. I mean, there's complicated stuff in the back here, but that's not required with simple electrolysis. You need basic stuff like this, like the voltage meter, the kilowatt. Here's my infrared thermometer. You can get one of these at Harbor Freight. It's got a laser, and you can check the temperature of fuel cells, check the temperature of electrical circuits. Here's another indispensable piece of equipment. This is to detect sine wave. Let's go over here. You can see the lamp running in my laboratory here. I can test sine wave and make sure I have an AC current flowing. So that device right there, I show you the oscillating current. You can get that at Home Depot. Simple books, guys. Simple stuff. Simple electrodes. They're also indispensable. I get those out of those 6-volt lantern batteries. Just some of the stuff, some of the lab equipment that you're going to need. Now we're going to test some of these electrical circuits, and we're going to see what everything pulls on the bench here. I'm going to show you guys what these fuel cells pull, what the laboratory computer pulls, everything. Anything I can dig out here. So remember, water, you know, it's a very powerful fuel. It's the most compressed fuel in the galaxy. This stuff is very compressed. A lot of people don't understand that. As far as we know, it's the most compressed fuel on the planet. So you can burn it again and again. It just turns back into water again. You got to remember that. It's an endless supply of constant and abundant energy. But you got to have electricity to get that out of there. And that's what we're covering in this video. Some of the basics of electronics. Basic stuff. And on my voltage meter here, you can see you can test for temperature too. They give you a thermocoupling. So the first piece of equipment that we're going to cover in this video is the voltage meter. Now this thing is indispensable. If you're going to get into electronics, even for a short while, you have to have this device. They're very cheap, easy to get, and you can see that it will measure the voltage coming right out of the sine wave circuit on the wall here. See, 120 volts. So you can use these probes right here to do just about anything you want. You can test anything. You can test batteries. You can test the wall circuit. You can test things you create. You can test solar panels. Think about this. You can do almost anything you want with that voltage meter. It's the single most important piece of equipment that you're going to have working with electricity. We're going to use that a lot here today. Let me film this so you guys can go back and read it. See, real quick, what I'm doing here is I'm using the sine wave from the electrical circuit from the house. I'm using that right now to charge my battery and turn that into a DC square wave. Because this is my battery charger right here, and this thing's got all the bells and whistles on it. It's a very nice one. It was pretty inexpensive too. I only spent about $60 on this thing back in the day. If you look right here, square wave is what I'm turning it into. I'm charging my battery. Now normally this battery is hooked up to my solar panels outside and I charge it, but right now it wasn't at a full charge, so I'm trying to charge it. So it's all about waves of energy, and being able to change those waveforms. You got to think about that now. You got to be able to take a square wave from like a battery. This is where you stored all your power from your solar panels, your wind turbines, your thermal electric generators. It goes to your battery bank. But then you want to turn it into a sine wave. And the reason you want to go from a square wave to a sine wave is so you can use your kilowatt system. You can send electricity over long distance as a sine wave. You can head out to your fuel cells. Now you could use a pair of jumper cables and hook directly up to this oxyhydrogen fuel cell right here, but I don't advise that because you're going to have a lot of sparks and things. These are really bad connections, these alligator clips. I mean, you could though. You could hook right up to this battery and it would run. But you want to have complete electronics control. It's very important to get your electronics down so you can get the plugs and the control that you need so you can operate these things with a switch. Think about that. You'll be able to operate things with a switch and have full control, full electrical control. And you do that through transformers, full bridge rectifiers, things like that. And that's how you control those waveforms. And again, the voltage meter plays a huge part in that, being able to detect these different waves. Sine wave, square wave. It's really simple stuff, guys, and the kilowatt plays a huge part in that because it gives you the ability to detect the amperage, the voltage, the electricity that's being consumed. So you want to have full electrical control. It's very important. That's why I'm talking about electricity in this video. And these frogs go way back. They know electricity better than you or I. It goes back to Egyptian times. And you know, these frogs, they study electricity. They study it better than me. The electron's always on his mind. See, he's studying the electron. He's staring at it. He knows. He knows he can take that electron and use it to split that water into oxyhydrogen gas. And as he studies that electron, he's going to come up with new ideas. So it's always on their mind. See, most technology out there works off of very low voltage, very simple technology. Even my largest reactor systems and everything, this is all low voltage. Everything you see here. I mean, there will be times where the voltage is raised. The voltage on electrolysis, even the large stuff, this runs off low voltage. I have everything out in the open here. I'm going to show you how it looks out in the open, where I'm just taking straight off the line circuit of the house. Now remember, this gets into electrical safety. When you're working with water and electricity, you want to make sure you know exactly what you're doing, because if you see people online, you'll see a lot of videos where people have high voltage transformers, microwaves, things like that. Never work with that stuff. It's very dangerous unless you know what you're doing and you have the experience. But what I'm going to show you here is this open on the table. You'll notice that I always have full electrical control. I have a PC power supply. Now on the other side here, that's the line circuit to the house. So you have to remember, it's always dangerous working with any electricity, but it converts it to a DC square wave. It's very low voltage. It's like a car battery. This is 12 volts. A lot of things work like that, but I'm going to show you right here. This is the 120 volt line circuit in the house. I have 2 electrodes in this water, and I was able to take a very small amount of electrolyte. I mean, that's how much I used to activate this water to get it to pull about 200 watts at 1 amp. And remember, a line circuit can pull 15 amps, 120 volts. That's 1,500 watts. I mean, that's just one plug on any house. That's why you have a 15 amp breaker. But I'm going to show you right here. I'm going to turn this on, and I've taken the full bridge rectifier, and I've taken sine wave and converted it into a square wave, so I can perform electrolysis. And I'm going to turn this on so you can see it. Oh, it's unplugged over here. Hang on. Safety plug. So see, that's going to generate an enormous amount of heat in there because I'm running a much higher voltage, and I'm pulling 1.5 amps at about almost 200 watts. So you can see the effect there. And you can take the line circuit and convert it directly into square wave, and you can perform electrolysis. Well, let's say I wanted to take that and break it down even further where it was more manageable and I can control it. Well, I could use a transformer. See, and I'm measuring this in sine wave, and I've broke it down to 12 volts AC. And then all I have to do is hook up my bridge rectifier, and then I'll have 12 volts DC. So you don't want to stick your fingers in this water, you would be electrocuted. It's the line circuit off the house. That's why you use power supplies, DC power supplies, so you have full control, full electrical control. No matter what you build, how big or how small. So I broke that down with the transformer, bring it to a more manageable level instead of having it at 120 volts. So your main reactor cores and your fuel cell production array is going to consume the most electrical power. And the way I'm doing this here is I'm taking the sine wave and converting it to a square wave using my PC power supply. This is how I like to do it. See, this isn't like I showed you before where you're using the transformer, the bridge rectifier, and you're plugging directly into the wall circuit here. I mean, that's one way you can do it. But this is the best way. This is a controlled power supply. It was designed to put out DC electrical power. It's very easy for me to perform electrolysis using power supplies like this. And of course, these could be made larger, they could be wired in series, wired in parallel. You could do all kinds of stuff. But I had to use a little bit more electrolyte. That's how much I used in that glass to get it going good, where I'm producing the gas. So it's something to think about. Your electronics are very important. That's a huge important part of electrolysis. And the more advanced you get and the better you are, the less electrical power you'll need to pull that water molecule apart. And that's what got Stanley Myers in trouble. He was able to break the water molecule apart using very little electricity. Think about that. Using less than half an amp. And he had a production at an enormous rate.